Okay, so today we're gonna do 2.1 matrix arithmetic. So we know what is a matrix. It's a rectangular array, right? So we had like that, rectangular, and then we have numbers, right? So if there is more than one, we call matrices, matrices. So more than one. Matrices. Okay, and then we introduce you about the row and column, right? So we have n by n with n by n. So this one telling us row, this one telling us column. Okay, so we have this one, 1, 5, 6, 2, 2, -9, 3, 8, 1, 4, 7, 2. So 3 rows, 1, 2, 3, right? So we said that 3 by column 1, column 2, column 3, column 4. So 3 by 4 matrices, okay? All right, let us just make that square matrix. So we have the same size, A equal to m by n size is called square matrix. So in other words, same number of columns and rows, right? Same number. Number of rows and columns. Okay. We talk about the entries too, right? So yes, the definition is a square matrix and entries. The individual element of matrix called entries or component. So we often use entries, right? Okay, we have ij entries. For instance, so we have ij entries. Okay, that is, the first one is I row. This is j column, right? Okay. We denote ith, jth. jth. So we denote this way. A equal to Aij entries, right? So if we say that A23, A sub 23, so means that this is a row 2, second row and third column, right? So column. So 2, 3. 2, oops, 2 and 3, right? So 8, 2, 3 entries. So that is 8. How about this? Opposite. 3, 2, what do you get? Third row and second column.
-9.
Excellent. Okay, so that is entries, right? Row, column. True. True. Okay, now. So we have zero matrix. So in this case, we have a 2 by 3. So that is 2 rows and 3 columns. So everything is 0, right? That is a 2 by 3, 0 matrix. Okay. Now, how to add matrix? Matrices. To add a matrix, they must have same size. So we talk about the size earlier, right? So for instance, n by n, right? Like a square matrix. Okay, so it's not that size. So it can be rectangular size, not square size, but must be have two matrix that has the same size. Okay, so let me write down. So they must have the same size. For instance, A has m by n, m, then B must be m by m. Or A has m by n, then B must be m by n, or A equal to m by m, B must be m by m, right? So they have the same size, means the same size. So definition, say nicely, let A equal to Aij entry and B equal to Bij entry, B to m by n matrices. So means that A equal to m by n, also B equal to m by n matrix, right? Okay. Then A plus B equal to C, we can add them. Also C equal to m by n matrix, right? So where C is m by n matrix and C equal to Cij entry defined by Cij equal to Aij plus Bij, right? So means we add them in the same position, which is same entry. Okay, all right, so let us do this. We have A equal to, and if possible. That means we have to check their size, right? Okay, A equal to 1, 1, 2, 0, 3, 4, and B equal to 5, negative 6, 2, 2, 3, 1. Okay, let's check the size. This is a 2 by 3, right? Row, column. And this is also 2 by 3, which is row, which is column, right? Okay, we can add them because their sizes are same, right? Okay, now we're gonna have the same 2 by 3. So C equal to, we add them. So we are adding same spot, means that their entry spot, right? So 1 plus 5, 2 plus 2, 3 plus 3. So 1 plus negative 6, 0 plus 2, 4 plus 1. What do you get? 6, 4, 6, negative 5, 2, 5, right? Okay. Now, we have a proposition. Proposition 2.1.1, properties of matrix addition. Let ABC be matrix. Then we have A plus B equal to B plus A, right? It's commutative. Of addition. Second one, A plus B plus C is the same as A plus B plus C. Parentheses there, associative of addition, right? Associative of addition. Okay, third one. We have A plus 0. We get A back That's the additive identity. Last one. We have a plus negative a gives the 0 additive inverse. All right. So we have another one, scalar. Definition, scalar multiplication of matrices. Okay, if A equal to Aij entry and K is a scalar, so scalar means number, right? Anywhere number. Then Ka equal to, we can make inside the matrix K times with that entry, right? Okay, let us do this one. Find multiplying by 7 result of multiplying the following matrix A by 7. Okay, so we have A equal to 2 by 2, which is 2, 1, 0, negative 4. Okay, we multiplying by 7, so we do 7A. So 7 times of 2, 1, 0, negative 4. Okay, that is, so we just multiply on the entries, right? So 7 times 0, 7 times 1, 7 times negative 4. So what do you get? So we get 14, 0, 7, negative 28. Yeah. Okay, now we have properties for scalar multiplication too. So let me write down proposition. Two point 1.2 properties of a scalar multiplication. Okay. Let A be R matrices. And K, P are scalars. And we have the first one, K, A plus B. We can distribute. So we get K, A plus K, B. And second one, we have, oh, this is distribute, right? Distribute. So we have scalar, K plus P. And we get matrix A. Then also we can distribute, right? So we have KA plus we have a PA. All right, so this is also distribute. Tiv row. So this is over matrix addition. This is over matrix addition, and this is over scalar addition. Okay, third one. So we have multiplication, right? So we have a KPA is the same as KPA. So we can put parentheses here. Yeah, okay. So this is associative in multiplication. Associative or multiplication, but they mentioned the scalar multiplication. No space. All right. Let us do that. Let us do 2.2. So multiplication of a matrix or the properties, right? So multiplication. Of matrices. Okay, so we have a matrices, right? Matrix, and then we have the n by 1 or n by 1, and we call the column vectors. So let me write down. So vectors first. Definition. Row and column vectors. We call that matrix of size n by 1 or 1 by n vectors, right? Okay, now n by 1, we say the column vectors. So we had the experience, right? So uppercase X, this book indicate the column vectors, right? So X equal to column, so n by 1, so X of 1, X of 2, X of n because n by 1, and so we called column vector. Okay, we have 1 by n. This is a row vector, so we denote it this way. They denote the same uppercase X. So uppercase X. So they're using row X of 1, X of 2, X of n. All right. So this is row vector. Okay, now we talk about the linear combination. So linear combination has the form, looks like this. So we have a 7, 1, 4 plus 8, 2, 5 and plus 9, 3, 6. Okay, there will be 7, 28. We get the 16, 40 and 20, 26, 53. Can you please calculate everything? What do you get? So we have a 7 plus 16 plus 27. Thank you. And can you please calculate 28 plus 40 plus 54?
I got 50 and 121.
50 and 141?
121.
121? Can anyone
Oh, wait,
confirm?
no, 122.
122. Thank
wrote-
you.
You meant 54, not 53. Right?
Okay, sorry about that. I'm looking at this one. There's a 53. So it's sorry, 50. Yeah, 50.
Yeah, 122. Yeah.
Okay, thank you very much. Okay, so we call this is a linear combination of 3 vectors. So we denote like coefficient, right? And then we have 3 vectors. So we can use a V1, V2, V3 as a vector notation later on. Or UVW, like a vector notation later on. Okay, so it's linear combination of 3 vectors. So we had it before, linear combination, right? This is the second time we are using that linear combination. Okay, now terminology. We have system of linear equation, and we want to express as a vector form. Definition. 2.2.2, the vector form of system of linear equations. Okay, so we have a sub 1, 1, x sub 1 plus a sub 1, 2, x sub 2, and x sub 1 and x sub n, right? And then other side constant term, which is b sub 1. Now a sub 2, 1, x sub 1, plus a sub 2, 2, x sub 2, we have a sub 2 and x sub n equal to b sub 2. All right, so do that. Then the row m1 x sub 1, a sub m2 x sub 2, and a sub m n x sub n equal to b sub m. So that is system of linear equation, right? Okay, now we want to express a vector form. So vector, which is vector form. We take out the x1, column vector will be, right? So a sub 1, 1, a sub 2, 1, a sub m1 plus x sub 2, and a sub 1, 2, a sub 2, 2, a sub m2. Okay, now x sub n, a sub 1 n, a sub 2 n, a sub mn, right? Okay, then the last one, the constant matrix, which is b sub 1, b sub 2, b sub n, column vector, everything. Okay. All right. Look, we had this formula, right? Okay, let's write down this way. That was column vector. So we do reverse. So 1, 2, 3, 4, 5, 6 as a matrix, right? And then 7, 8, 9 as a one matrix. Okay, so let us do this. Okay. Express other way. So we have 1, 2, 3, 4, 5, 6. So we get 7, 8, 9. Okay. So this one, how we did? This one we did 7 out, and then we did 1, 4, right? And we did 8 out, 2, 5. We do 9 out, 3, 6. Okay, so I believe we get the same answer. Yeah, look, it's the same, right? So we get 50 and 122. 50. 122. So what is telling us? We're telling us we can operate this one that way, right? Never mind. So we have a sub 1, 1, a sub 2, 1, a sub 1, 2, a sub 2, 2, a sub 1, 3, a sub 2, 3. And we get x sub 1, x sub 2, x sub 3. All right, so this will be x sub 1, we have a sub 1, 1, a sub 2, 1, plus x sub 2, a sub 1, 2, x sub 2, 2, and plus x sub 3, a sub 1, 3, a sub 2, 3. Okay, we multiply everything and add them. So this one, we can do the a sub 1, 1, x sub 1, plus x sub, a sub 1, 2, a sub 1, 2, x sub 1, x sub 2, one, 2, x sub 2, plus a sub 1, 3, x sub 3, and a sub 2, 1, x sub 1, plus a sub 2, 2, x sub 2, plus a sub 2, 3, x sub 3, right? Okay, let us do this one. We have compute the product AX for, okay, A equal to 4 by 4 matrix. So, sorry, 3 by 4, 1, 0, 2, 2, 2, 1, 1, 1, 4. Okay. 3, negative 2, 1. Okay, X equal to 1, 2, 0, 1. They don't talk about the size yet. Okay, so after this, they're gonna talk about the size. All right. Okay, how do we multiply? So we take out 1 and we multiply, right? We take out this, we multiply, we take out this, multiply, we take out that, multiply, right? Okay, let us do that. So AX equal to 1, 1, 0, 2, plus 2, 2, 2, 1, 0, everything is 0, plus 1, 3, negative 2, 1. Okay. So let us do, can you please calculate? 1 plus 2 times 2 plus 0 plus 1 times 3 and 0 plus 2 times 2 plus 0 plus 1 times negative 2 and third row 1 times 2 plus 2 times 1 plus 0 plus 1 times 1, right? What did you get? So 8. Excellent. 8 to 5. Thank you, Mrs. Okay. Let's move on. This one is a matrix form. Matrix form. Okay, we have to write down. So I'm gonna just write down whatever we have. This one, I'm gonna make it just short. Just change that. Just change the title. Come on. Hey. Okay. Listen. So matrix form. Okay, so 2.2.4. I don't know what was the 3. Matrix. Okay. So matrix form. So earlier we had a vector form. Okay, now we are writing down a sub 1, 1, a sub 2, 1, a sub m1, a sub 1, 2, a sub 2, 2, a sub m2, a sub 1 m, a sub 2 n, a sub m n. Okay, now a sub x sub 1, x sub 2, x sub n, and constant b sub 1, b sub 2, b sub n. Okay, now multiplication, how to multiply two matrices, right? Okay, let us talk about that. So when we multiply, matrices. Okay, so we have to have a match inside the size, means that we have a equal to m by n, b equal to m by p. We want to multiply, right? Look, so m by n and m by p. So this one must be matched. So we will get m by p, right? So for instance, pick a number. 3 by 2, b equal to 2 by 3. Then we multiply, what kind of size we get? This is a match, right? So we will get 3 by 3. Pick a number.
About 4 by 5.
4 by 5. We get b equal to 5 by 2. So what kind of size we get?
Four by 2.
4 by 2, excellent, yes. Okay, how about this? Last one, we have 4 by 5, b equal to 2 by 5. What kind of size we get?
4 by 2 again? Or does it not work?
Does not work. Impossible,
Okay.
right? Impossible. It must be matched like that. Okay. All right. We're gonna learn about more multiplying two matrices. But then let us do one more just today, and then we do next time. So find BA if B equal to 1, 0, negative 2, 2, 3, 1, 0, 1, 1, A equal to 1, 0, and 2, 2, and 1, 1. Okay, so every time when you do add, subtract, and multiply, we have to follow the size, right? So addition, subtraction must be they have the same size of each matrix, right? And multiplication, we can check the column of A and column of column of A, row of B, right? So inner, we have to check that. In that case, it's a BA, right? So this is 2 by 3 matrix. This is 2 by 3 matrix. Can you multiply?
Wait, I think you wrote that down wrong.
Did I make a mistake? Yeah, I made a mistake, correct.
3 by 3 and 2 by 3.
So yeah, I made a mistake. So 3 by 3, right? 3 by 3. I made a mistake.
I don't think we can multiply those, right?
Yeah, we cannot multiply because this one must be matched, right? So the size is not matched. So cannot multiply. Okay. All right. Any question? Okay. Thank you for coming.